Okay, now our discussion will be on thin film interference or thin layer interference. We first need to understand how waves can interact with a reflection from a medium. If you take a look at this picture on the right here, we have a wave coming in. It's oscillating up and down and up, and it collides with a wall or a pole or something, and it reflects back. And notice how this is a 180-degree phase shift. What that means is it reflects back. This one's down, and then this one's up, and this one's down. On the way in, it was up, and then down, and then up. Now it's down, up, down. This happens for light waves as well. Anytime a light wave is going from an index of refraction smaller to an index of refraction larger, and it reaches that interface between the two actions there, it'll be reflected back 180 degrees out of phase. The refracted wave will not be affected though. So let's take a look at this picture here. Here's an incident ray coming in from air, index of refraction of 1.00293. It reaches maybe a soap bubble or something like that. Index of refraction is greater, so the reflected ray is going to bounce off here out of phase, 180 degrees out of phase. The light that goes through refracted will not be out of phase, and then the light that gets refracted here will also not be out of phase. So what kind of thing does that create? Well, if you have waves that are out of phase and waves that are in phase, when they interact with each other, they will interfere with each other negatively and produce darks. Let's see in this next example here. So here's our incident ray coming in. Okay, air being about 1.00293 index of refraction. Water or glass here, this is going to be an index of refraction greater. So when this light ray gets reflected, it is going to be 180 degrees out of phase coming off here. The light ray going through is refracted and will not be out of phase. It reaches the other side of the thin film or thin glass, whatever it is. It's now going to bounce back this way. Why? Because it reached the interface. But now it's going from an index of refraction greater inside versus outside. So this will not be 180 degrees out of phase. It's going to reach this layer here and then refract out back into air. When these two waves overlap each other, this will be out of phase, this will be in phase, and this will produce a dark. And that's how interference occurs. And there's a generalized equation, okay, that we use in order to figure out how this is going to interact. We're going to call the distance between the layers, this is air and then air, we're going to call that T. And T is for thickness. There, of course, will be index of refraction N inside here. Okay, and then there, of course, will be a wavelength of light coming in. So how do we figure this out? Well, because these two are out of phase with each other, the equation is going to be this. It's going to be 2nt equals m lambda. And m is going to equal 1, 2, 3, etc. And these are bands, just like there were bands in the single and double slit, okay, diffraction patterns that we saw before. Now, why is it 2nt? Well, this light ray has to go in one distance, thickness t, and then come back another distance t, and there's an index of refraction n inside this material. That's what this n stands for. Well, the extra path difference that this goes through, when it reaches the other wave, because they are out of phase with each other, that'll produce a dark. So in this particular case, this equation will produce a dark. Okay, but what about brights? Okay, well, the same equation would apply to nt equals m lambda. These will produce brights if we have an index of refraction greater here and greater here also on either side of this. Okay, let's say we have some kind of oil on either side of this, and we're seeing that the oil is greater index of refraction here versus there. Well, if that occurs, then we will not see, okay, darks, we'll see brights. Okay, why would that be so? Well, because this right here, okay, will not cause a 180-degree interphase change, nor will this one. So they will come out to each other, in this case, as brights. So this is our generalized equation, okay, for bands that we want to find either darks or brights, okay, depending on what's happening. Now, of course, we can use the equation 2nt equals m plus 1/2 lambda, in this case, and then m could equal 0, 1, 2, 3, etc. Okay, this one here could produce darks or brights depending on the situation. Is the wave 180 degree out of phase, or is it not reflected 180 degree out of phase? So it's all going to depend on what happens. And we'll do some examples to help you understand. So what does thin layer interference look like? Well, you might have witnessed it before if you've seen a soap bubble. Here's an example of a soap bubble. And notice the patterns here. And we see different colors in there because there's different thicknesses in a soap bubble. So this is a good thin layer interference. You might have seen this on asphalt before when there's a little bit of oil and water mixed from cars and you see colors of rainbow, okay, on asphalt in a parking lot or something like that. So this is a good example. Of course, we'll do actual example questions in my next video to help you understand better.